So if there's no friction and imagine it like someone on a roller skate. Okay. So the force can only, so there's a force that keeps the roller skate from sinking into the ground, right? So there has to be a force perpendicular, but since there's no friction, there's nothing perpendicular to that. If this person tried to accelerate into the surface, there'd be a force preventing that. But if this person tried to accelerate this way or this way, there's nothing to do that. So that's why if there's no friction, the force is just perpendicular to the surface.
So, but if you were expressing it as a vector, would you want to have the negative sign?
You would have, so in a free body diagram of this person, the force would just be this way. And yeah, if your coordinate system is the standard axes, then yeah, that would have a negative x component and a positive y component.
Sure, but in those free body diagrams, like in the homework, you're just kind of like expressing it as like...
You're just drawing the direction, but the direction you draw should always be perpendicular to the surface. And then for when there is friction, I mean, you remember from physics 1, there's a normal force, and then there's a friction force that the direction can be different depending on what's happening. And since we don't know what the ratio is of the normal force and the friction force, the best we can say is there's forces in both of those directions. And there's no point for us in this class in breaking it up into a normal force and a friction force because, I mean, okay, so think of it this way. Depending on the magnitudes of these two, this could be any direction, right? Like you could have this, and then that comes out to be a force in that direction. You could have this and this. That's a force in this direction.
So then the negative sign would come from your sine and cosine of the angle rather than the...
Yeah, except the thing is, right, so it can be this whole infinite range of directions if it's going, if there's something causing it to act the other way, it would be like this. There's this whole 180-degree range of directions. And so in whatever coordinate system we're in, we're just going to call that an unknown x and an unknown y component. Does that help with that?
Yeah,
okay.
Yeah, the question was just about the friction slugs.
Okay, yeah, right. I mean, just think of if there's no friction, there's no way to, I mean, if there's no friction, like you can't walk or anything, because you can't generate a force parallel to the surface, you just like moonwalk.
Put it in there because we're getting a scalar and then we're going to put the angle in there.
Right, correct.
We actually have another question.
Yeah.
On the homework,
yeah.
There's an additional force on...
Okay.
That's 20 kilograms.
Kind of just a red herring, right?
Let me look. I wonder if sometimes like I'll change questions and then the solution won't get changed or something. Let's see what's going on.
That's at least what I assumed when I was looking at it, because that force would just be eaten up by the normal. And since the normal is unknown, right?
I think it would add to the weight for it, because it's 20 kilograms, putting on 10 kilograms.
Right, but it wouldn't change the gravity force.
This?
Yeah.
Okay, well...
Mine's kilograms, not newtons.
Yeah, it's kilograms.
Oh, okay. I guess the one that's on B2L is just wrong, needs to be updated. Yeah, right. It shouldn't be kilograms. That doesn't make any sense. Free body diagrams would never have anything but forces and couples on them. Okay.
Okay.
Okay. Yeah. Well, so I need to change that. All right. I'm gonna make a note of that.
B doesn't even have it either.
Okay. All right. Any other questions?
Those were both of my questions.
Okay. And so today, I guess we're just going to go into mostly, well, let's just do some example problems. But first, I want to show you something that you're not going to need yet, but I want to show you something because it's cool. And later on, I'll go into it again, and then you'll need to use it. So this is the cool kids way to change coordinate systems. So, in physics 1, when you did block sliding down inclines and stuff, you always chose a coordinate system with the y-axis perpendicular to the surface and the x-axis parallel to the surface, right? And you did that by setting up a triangle and figuring out, and it's not like horribly hard, but there's a much simpler way to do that using a graphing calculator or any calculator that can do vector stuff. And that's rotation matrices. So say that you want to go, we're just going to do this in 2 dimensions. You can also do it in 3D. But in 2D, say you know all your vector components in a coordinate system like this. And you want to express them in a coordinate system like, so let's say here's the horizontal, and you want to express them in a coordinate system like this, where this angle, the counterclockwise angle from the old x-axis to the new x-axis is theta. Okay. So theta is the counterclockwise angle you need to rotate the original coordinate system to get the new coordinate system. Okay, you with me on what I'm talking about so far? Then we're going to define a rotation matrix Q as cosine of theta, sine of theta, negative sine of theta, cosine of theta. And for every vector, the new components of the vector are just equal to that rotation matrix times the old components of the vector. So I'm going to tell you how to multiply matrices for people who haven't done that before, but your calculators will just do it for you with the with the regular multiplication symbol, so you don't even really need to know, but
And that'll be the dot product.
that is just multiplying. So you can just do it like you're multiplying numbers and your calculator will do it. Here's how it works. So if you have A, B, C, D multiplied by E, F, the vector you get out is, so you can think of it as a series of dot products. First, it's the dot product between this row and this vector. And so that comes out to be AE plus BF. And then the second one is the dot product of this row and this column. So that is CE DF. So in 2D, it's not too hard to do this by hand. In 3D, it takes more time, you know. But your calculator will do it instantly in any case. So let me show you how this works in like a block on ramp problem that you're familiar with. So let's say that there's the ramp. Let's say this angle is 25 degrees. Let's say it's 30 degrees so I know what the cosine and sine are without multiplying them. And let's say that you have this block that's 10 kilograms. And let's say that you want to use a coordinate system that's oriented with the ramp. Okay. I guess for now I'll make this frictionless. Okay, so a free body diagram of this block. We have the weight down, that's 10 times 9.81, so 98.1. That's a frictionless contact. You know, now we're just going around the boundary looking for contact. So it's perpendicular to the surface toward the chosen body. I'll call that N. Okay. And now we want to go to Newton's second law. Well, in this rotated coordinate system, that N is easy. That's just in the positive Y direction. But if you remember the thing, when you rotate these coordinate systems, then the thing you have to worry about is the weight force, you know, then you have to come up with the components for that. Remember all this? Anyone? So what we're going to do is we're going to find the rotation matrix that goes from this to this. Okay, what's the counterclockwise rotation that you have to take the one on the left to make it the one on the right?
30.
Yeah, positive 30. Okay. And so the rotation matrix, the undersquiggle thing is the just matrix symbol to tell you that's a matrix variable. So this is equal to cosine of 30, sine of 30, negative sine of 30, cosine of 30. And that is 0.866, 0.5, negative 0.5, 0.866. Okay? And so mg in the new coordinate system is just q times mg in the old coordinate system. And that is 0.866, 0.5, negative 0.5, positive 0.866, times, what's mg in the old coordinate system?
0, negative 98.1.
Yep, right, exactly. 0, negative 98.1. And so do this multiplication. Negative 49.05, negative 84.95. And you can see that at least, that makes sense with, if this is the coordinate system, we know that this vector, this weight force vector, is going to fall in that third quadrant over there. So it makes sense anyways. The first few times you do it, there's no reason to believe that this is any faster than the way you did it before, but especially if you have a program built into your calculator to do it, and even if you don't, once you start getting used to this, it's just a fast way to do this stuff. And so, now this is what we could use in Newton's second law. We have 0n plus negative 49.05, negative 84.95 is equal to 10 times a0. And then you can solve all this stuff. Okay, so later on we're going to use this. For now, we're not going to use it. The reason we're not going to use it now is that we don't have to do anything in a rotated coordinate system for stuff like this. There's no benefit to it. So we would just keep this in our old coordinate system. But anybody have any questions about that right now?
Is it possible to store that as like a function?
Yeah, totally. Yep.
Like almost like a
And so-
variable or something?
Yeah, I mean, I've always done it, depending on your calculator, I've always done it on the older TI calculators as a program. And so you call the program, enter in the angle, and it just spits out the matrix. And then you can just hit the times button and go straight to multiplying by your vector, and it makes everything really fast and easy. And there are instructions for how to write that program and stuff in the, I think on D2L there's notes, and then if you go to that textbook, those textbook PDFs, there's an appendix that tells you how to do that too. Okay, let's do a couple examples. So the first one, this is called the block and tackle system. You've probably heard of pulley advantage before. And then I remember when I took physics for the first time and we talked about pulleys, I was confused because I knew sort of vaguely that this pulley advantage could reduce the amount of force that it required to lift an object. Maybe you've heard of that before. But then when we talked about it in physics, it's like, oh, well, all this pulley does is change the direction of the force. So I was confused, Well, it's not really the pulley that makes it so you need less force to lift something. It's a specific configuration of pulleys. And so here is the way it works. If you have a pulley connected to a wall or a ceiling like that, and then you have another pulley that isn't connected to the wall or the ceiling, that's like just a hanging pulley that's supporting a mass. So let's say that this is 10 kilograms too. And a cable goes through this system. And then, something's supporting the weight of this mass by applying a force T to this cable, okay? The question is, what force T is required for static equilibrium? If this was, so first, if this was just a single pulley with the mass on one side and T on the other side, what would this force T be? It would equal the weight of this, so it would be 98.1 newtons, right? We're going to see that it's less than that in this case. Okay. So I'll start with a free body diagram of all the hanging stuff. And so I think a nice way to think about that is, okay, so when you're thinking about a body to isolate, you can isolate any body that you could imagine putting a boundary around, a closed boundary around. So here's what I'm going to isolate. Bless you. All the stuff in red, that's going to be my free body. Okay? So notice that this includes the part of the cable that goes under the pulley. And I have it including just a little bit here too. And then all of this stuff. And we're assuming that the pulley is massless and frictionless and that the cable is massless. So that's not going to add any mass to this thing. And so my free body looks sort of like this. Okay. The weight force is 10 times 9.81. And now we have to come up with the contact forces. Well, this is a pulley force connecting this part of the cable, cable force applied to this part of the cable that we're including by the part of the cable that we're not including. So what's the direction of that force? It just follows the cable rules. So it's going to be parallel to the cable, away from the chosen body, and that has to be this. Okay? And then the other one, same thing. That's a cable force. So it's parallel to the cable, away from the chosen body. It's the same cable, so it's the same T, as long as there's no friction and no masses and stuff like that. And so now we'll go to Newton's second law. And we have one force, 0T. A second force, 0T. A weight force, negative 98.1 in the y direction. And we're looking for this to be in static equilibrium, so the acceleration is 0. You get one equation that just says 0 equals 0. But the second equation says 2t minus 98.1 is equal to 0. So T, the T required, the force you have to apply to hold up this weight of 98.1 is 49.05 newtons. Okay, so that's pulley advantage. It's not a property of pulleys themselves. It's a property of a clever configuration of pulleys. Okay, let's do a similar one. Um, so this time we have the single cable that goes all the way through this system. And we want to know what's T for static equilibrium. And so we're going to use the same approach again. We're going to isolate all the stuff that's hanging, all the stuff where if that cable was gone, what would crash to the floor. Okay, so so that's what I'm isolating. It looks like a block-shaped guy at like a really good rock concert. Okay, so 98.1. And then these are all just cable forces. It's the force applied by part of the cable to the other part of the cable. So that's T, 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 T. And so you can imagine, I mean, we could write it out in vector form, but it's going to work just like this. This was 2T is equal to 98.1. This is 4T is equal to 98.1. So T is equal to 24.525. And you can imagine, theoretically, you could keep putting more and more pulleys in this system as long as you keep using this same idea, this same configuration idea, and you'd keep cutting this in half with every new hanging pulley you used. Well, not in half. No, you would be dividing by 2 more each time. So the next hanging pulley we apply would be 6T. You know, it would be the weight divided by 6, and then divided by 8, and then divided by 10.
Doesn't that same principle apply to how much the lift and load moves as you pull on the?
Yes, that's a really good point. So we're doing static, so I didn't talk about how much. I'm just talking about what you have to apply to, like somebody's like, I gotta go to the bathroom, hold this. That's how much force you'd have to hold. But if you wanted to lift it up, so you don't get any energy for free. There's conservation of energy. So if you wanted to lift this thing up a certain distance, it doesn't make sense that you'd have to apply the same amount of work, that you'd have to apply less work. It doesn't make sense that way. You have to apply the same amount of work to do the same amount of work. And so the trade-off is you'd have to pull it twice as far, 4 times as far, 6 times as far to get it up. It's like bicycle gears, you know? Like you can make it take less work to pedal up a hill, but then you got to pedal more times to get the same distance. Yes?
Obviously for the Siga class, we're not gonna have stacked pulleys.
Yeah.
Would it ever be acceptable to change the outline.
Yeah, for sure. This is a very inefficient way to use space, and so these are used in like different types of loading. You know, in shipyards, you see these like if you go to the docks at Duluth, you see these set up everywhere, but they don't look like this. They're all just like everything's folded into a line into the page, and yeah, you can do that. But the key thing is that you have half of your pulleys connected to the whatever's bearing the load, and then half of your pulleys are just hanging from the cable. And the whole contraption, this block and tackle contraption, just shortens as you pull the thing up.
If the red outline were, for whatever reason, inconvenient to draw the three-body diagram, or is it all right to modify the shape?
I don't follow that.
I mean, here it's already done.
Yeah.
But like if it were stacked.
Yeah, okay, yeah. Oh, I got you, yes. Yeah, I think I do that kind of stuff a lot. Like when you switch from 2D to 3D, free body diagrams get a lot more complicated to draw. And yeah, like there are definitely times when you would just change the shape of stuff to make sense out of it in your head. Yeah, for sure.
Okay.
Any other questions about that? Okay, I want to do, just to beat this horse to death, I want to do one more example like this. So let's say, notice that this really simple math here all has to do with this, the separate parts of this cable being vertical, okay? So let's see what happens when those cables connecting the pulleys attached to the ceiling to the hanging pulleys move away from vertical, okay? Let's see what happens to that force. So I'll just go back to 2 hanging pulleys again. Okay, so or 2 total pulleys, I mean. So let's say this is 10 kilograms, and let's say that this angle now is theta. Okay, in the last case we did, that theta would have been 90 degrees, and that has to equal this one in order to get equilibrium. And it would have to equal this one too if this wasn't rigid. If the connection between the ceiling and this pulley is rigid, then that angle could be anything. And let's calculate what this required T is, and then see what happens in the limit and stuff like that. Okay, so the free body diagram, I'm going to isolate all of the hanging stuff again. So we have this pulley, the little bits of the cable coming from the pulley. We have the weight force of 98.1. A force T here, and a force T here. And this angle is theta, and this angle is theta. So Newton's second law says For the one on the right, this is t cosine theta, t sine theta. For the one on the left, this is negative t cosine theta, positive t sine theta. You see that? And then the weight force is 0, negative 98.1. The x equation, notice that the t cosine theta and the negative t cosine theta, those cancel out. So we get 0 equals 0 again. But the y equation says 2t sine theta is equal to 98.1. And so t is equal to 98.1 over 2 sine theta or 49.05 divided by sine theta. Okay, so if you got to choose this angle theta, what's the smallest t that you could, so if you chose the optimal theta, what would you get for t at its smallest value? 49.05. Yep, that would be the case where that theta is 90 degrees. That's right, the one we did before. If the worst case scenario, what would you get for t? Well, you know, as that angle goes towards horizontal, that t gets bigger and bigger and it goes all the way towards infinity. So,
you have better off just lifting it yourself.
yeah, so you might think like, oh, the limit would be to go to the case where you didn't have this block and tackle. It just goes to the weight of the thing, but it gets way worse than that. So
I guess how in practice though, then, I mean, because I can just imagine pulling on that thing and it being flat. You know, and it's like,
yeah.
I wouldn't have to put an infinite amount of force on it.
You would have to. You can imagine it, but your imagination is messing with you.
So what you're saying is no matter what you do, it's always going to have some small
Yeah,
angle.
That's right, yeah.
You'd probably be able to get it really close. The last
Depending-
couple degrees would be
yeah,
ridiculous,
That's right,
though.
yeah. That's true.
It'd be an exponential curve, right?
What would it be? Do I know what that would look like? Well, it would be a cosecant curve, I guess. It would be 1 over sine curve. But I can't picture what that looks like. That's like it's the u and then the upside down u, right? Isn't that secant, cosecant? But anyways, yeah, it would change fast in the last few degrees. You're right. Okay, any questions about that? The next thing we're going to get into, so I'm going to give you a bunch of these particle problems to do, but then the next thing we're getting into is rigid body statics. Do you remember in particle statics, the first thing I said was that the equations of motion, there's no motion, but what we're calling the equations of motion are just Newton's second law. So in 2D, how many equations do we get? 2. And in 3D? 3, right. So now the equations of motion are going to be F net is equal to 0. And that is 2 equations in 2D and 3 equations in 3D. And the moment, the net moment about any point A is equal to 0. And that is going to be 1 equation in 2D and 3 equations in 3D. Okay, so now we're going to have to deal with 3 total equations.
Is that a double subscript?
It is, yeah. 3 total equations in 2D and 6 total equations in 3D. There are some nice things about starting with statics before you go into dynamics, but there are a couple of places where learning stuff from statics gives you really bad habits that then you have to unlearn when you go to dynamics. And this is one of those cases. So I want you to keep this in mind. And when you took physics, you might have called this torque more often than you called it moment, possibly, but that's what I'm talking about, what you called torques. In engineering, you tend not to call them torques because a torque is a specific combination of moments. But what I want you to notice is in the static case, so in statics, the about point of your moments, that point that you're calculating your moments about, can be anything. You can choose any point you want, on the body, off the body, doesn't matter. In dynamics, the about point can only be 2 things. A still. It can only be the object's center of mass, or second, a point on the body that's fixed in the coordinate system. So that would be like an example of that would be a pin joint connecting a body to the ground or something. Okay. So we're going to take advantage of this in statics, that we have this extra flexibility to choose where we're calculating our moments around. But remember that in the more general case, you don't have that flexibility. Okay, so the first thing we have to do is define the moment. And I want you to sort of keep in mind that this moment, people just call it a moment, but that's really a shorthand for the moment of a force about a point. And so what that force is matters, and what that point is matters. Okay, so let's think of a general body. And let's say that our about point is A. So A is the coordinates of that point. It's also a vector that goes from the origin to the point. And we have a force applied somewhere else. So this is the force vector F. And the point where this force is applied, I'm going to call P. So A is the coordinates of the about point. P is the coordinates of the point where the force is applied. Then we can define a vector that I'm going to call rho that goes 2p from A. Oh, hold on. Okay, so draw a line between these 2 points. This vector going 2p from A is called the vector rho, the Greek letter rho, like a script EP kind of. So this is the coordinates of P minus the coordinates of A, and it's the vector to the point P from A. Then the definition of the moment produced by that force about A is rho crossed with F. And the intuitive meaning of that you can think of like a big wrench turning a bolt that's stuck. You know intuitively, like if you're having a hard time getting this loose and you're only so strong, let's say you can apply 500 newtons of force or something is the most you can apply. Well, your best chance of getting this unstuck is to apply that force down all the way at the end, right? You can apply that same force here, but it won't have the same likelihood of turning that bolt. And if you applied that force all the way here, you could apply 1,000,000 newtons of force right over the center of the bolt. Eventually the bolt would strip off of, it would break that thing, but it would never turn it. And so what's going on here is this is your point A. This is your point P. This is your force F. And this is your rho vector. Yep.
Are we deliberately choosing points as far apart as possible?
Yes, what you want, so the way this cross product works, you're not going to use this for calculations, but the magnitude, okay, so the magnitude of M is the magnitude of the force times the magnitude of that rho vector times the sine of the angle between them. So you want this rho vector to be as long as possible, But then you also want that row vector and the force to be perpendicular to each other. That's the way the cross product works. Remember, the cross product always, well, yeah, forget that. So you could have that row vector be really long and still not produce a moment. This is another thing that I think makes sense intuitively to everybody. Like if you just stood here pushing on the end of this, it would never turn, you know? Because your, the sign of the row vector and the force vector would be 0.
Are we choosing P and A or are we being given P and A?
You're not choosing P because the force is what it is. But in this class, you are choosing A. You can put A wherever you want. But it has to be the same for everything. So you can, if there's a million forces on a body, you can choose your A to be where it cancels out the moment of one force, but then all the other ones are gonna depend on that.
So if you chose an A in the middle of the wrench, your one component would just be 0.
Say it again.
Well, like if your A was in the middle of the wrench, how do you ever turn the bolt? If
Yeah.
your about point is in the middle of the wrench.
Well, if your about point is here, remember that there's also a reaction force. So if your free body diagram, let's say the stuff that you're including is the bolt and the wrench is one thing. Remember, there's a reaction force from the wall onto the bolt. And so if you're applying a force down this way, that reaction force has to be this way. And so you're getting half of a moment, half of our original moment turning it this way. And that reaction force is
The
causing
other
an
half.
equal, yeah, right.
So there'd be kind of like 2 A's.
Well, there's only one A, but depending on what A is, like, it just changes the values of all those moments, and it happens to come out. I mean, not happens, but it's not super intuitive that it's going to, but it does always work out. Yeah. Oh, we're over. Anybody have any other questions? Okay. We'll keep going with this next time, and I'll give you some more particle problems over the weekend.
Do you have time to explain the equation for the coordinate system